Is it okay if we turn the pre-lab in or turn it out?
I'm fine with that.
Okay.
Just so long as it's not the jazz approach to displaying data. And I mean by that is a little bit of your work's here, and then a little bit of your work's over here, and then the rest of it's over here, and then the next problem's here, here, here. Like jazz. Was it Kenneth?
Yes, sir.
All right. All right, so I'll make up different numbers. Just give some illusion of it. I'm not teaching to the assignment. All right, so we have, now the mass of the two balls is completely irrelevant in terms of what I'm asking for in the problem. So we have a ball that's dropped from a height, we'll just say 10 meters. And the moment it's dropped, another ball is shot up into the air. And then they land at the same time? Yep. So we're trying to find some initial velocity here. And so this is green and red. As with any of these motion problems, we've got 5 basic characteristics. Displacement, initial velocity, final velocity, acceleration, and time. If I know 3 of these things, I can find the other 2 if acceleration is constant, which it would be in this problem. Because once it's in the air, as long as we can ignore air resistance, acceleration is going to be so close to constant that we are safe in saying that it's constant. Now, in reality, acceleration does change depending on how far you are from the surface of the Earth. But in order to know, let's say from the top of the building to the bottom of the building, in order to be able to figure out the difference in the acceleration at the top and the bottom, you need multi-million-dollar equipment. It is that close to at the top and the bottom of this building. Matter of fact, you're pretty safe in anything that you're dealing with in everyday life. Even in an airplane, the acceleration in an airplane, acceleration to gravity in an airplane is still close enough to what it is at the surface of the Earth. All right, so we have green and red. Well, first thing we need to do in a problem like this is decide what's the positive direction. Any opinions, desires?
Downward.
Sorry?
Downward.
You want it downward positive?
Yeah.
Okay. Why?
You should give an opinion on the problem.
Okay.
Both balls be going down eventually.
True. True. Since downward's positive, which of these variables do we expect to be positive? We'll just start out with, on the green side, will the displacement be positive or negative?
Positive.
Yeah, it ends up below where it started, and we said down was positive. Initial velocity? Final velocity?
Don't know yet.
Positive or negative?
Positive.
Okay. Acceleration?
Positive.
Time?
Don't know.
Pardon?
Don't know. I don't think this is it. Yeah, don't know it yet.
Positive.
I hope so.
Oh, I was just talking about the number.
We could set it up so time is negative, but that means that we set time is equal to 0 at some point in the future. All right, for the red ball, the displacement?
Zero.
Yes. It ends up back where it started. Initial velocity?
Negative. I don't know.
It should be negative because it's being shot up into the air. Final velocity?
Positive.
Yeah, because it's falling at that point. Acceleration?
Negative.
Why?
Because it's going up. And Down is positive.
Because it's slowing down.
Oh,
Acceleration deals with change in velocity, doesn't deal with the direction an object's moving, it deals with how velocity is changing.
Positive and negative at different points.
So when is it positive and when is it negative?
Positive when going up, negative when going down.
All right, so if acceleration is the same sign as velocity, what's going to happen? Okay, and if they're opposite, if acceleration and velocity are opposite? Okay, so let's go with what Riley said. As it's going up, you said it would be negative acceleration?
I said positive.
You said acceleration is positive going up? Okay. The velocity is negative while it's going up. And you said the acceleration would be positive, so it slows down. That makes some sense. As it falls, so it gets to the peak, how fast is it going at the peak?
0.
Okay? So it stops at the very peak just for a brief moment, maybe. And then it starts to fall. And you said as it falls, the acceleration is negative. So acceleration is negative, velocity is positive. What's going to happen? If acceleration is negative and velocity is positive, what should happen?
Cancels it out.
Pardon?
Cancels each other out.
In terms of speeding up or slowing down.
Slows down.
But if it stops at the peak, how can it slow down any more than that? Potentially a philosophical question, and I'm sure some theorists have tackled it, but I have no idea what it means to slow down if you're already stopped. So, as it falls, it's speeding up. Velocity is positive because of Rayon. Acceleration is also positive. Matter of fact, acceleration is positive the entire time. And then time, somebody said it very weakly, slightly better. Come on, like you mean it. There we go. All right, so now let's fill in a little bit more. My acceleration, we assume that this takes place on Earth. Did I state that or just assume it? Green ball dropped from a height above the ground. I didn't specify, but if in doubt, ask or I think generally assumed is taking place on Earth. Because everyone knows that red balls and green balls only exist on this planet. Therefore, it has to be Earth. I think you can check me on that one. I'm sure somebody's done research. Why 9.8? Because that's what?
Gravity is equal to
See if we can work on the wording.
Acceleration due to gravity
Yes.
in the positive direction.
We're eventually going to head over to the other room where there's two signs up on the wall that says G is not gravity. This is the acceleration due to gravity, which on Earth, that's the word Earth, is approximately 9.8 meters per second squared. What is it in Winston-Salem? Somebody's going to have to talk louder. Suddenly you hear whispers.
Is it 9.8?
Only if you round off.
5.79.
Say it again.
5.79.
It's closer to 9.8. Winston-Salem, it's 9.798 meters per second squared.
Why is that?
In general, the acceleration due to gravity deals with the amount of mass and the way the mass is distributed underneath us. Now, is your question, why is it that specific number, or how do I know it's that specific number?
Well, if it's always 9.8, why is it that number here?
It's not always that number.
Oh, okay.
It's approximately. World average is 9.805, but Winston-Salem, we're special. It really does depend upon where you are on the Earth.
how did you get that number?
So I looked it up. Now, I've done various experiments. I'm trying to see if I can actually hit that, but it's a physics experiment, so what are the odds that I'll actually hit that? And I can. The Silas Creek is there. And as you come down Silas Creek from the mall, you pass over Miller Street, and then the next road on the left, I can't remember what the name of it is, but there's the next road on the left. If you follow that road where it hits Silas Creek, right there in the median, there used to be an official piece of equipment that was testing the acceleration due to gravity here. So we have a much more accurate value than most places because they don't stick them everywhere. They just stick them very key locations. And so we actually have it within throwing distance of this building. About at this height, maybe a little bit lower. And then since they went through that experiment, they've now taken planes and they've flown planes all over the world. And about 10 years ago, they finished mapping the entire world. So, and I looked it up on that way too, and got pretty much the same thing. And then there's a formula assuming a smooth Earth, but bulging at the equator, and I got pretty much the same value there too. Other questions at the moment? All right. So, by the way, usually it's in the notes section of the lab. If I have it in there, I will specify what value to use for G. So if you see this number right here, that's because it's the Winston-Salem specific. If I don't specify and you have freedom to choose it, please do not use 9.81. It's a world average. I mean, I'll go with 9.8, but not 9.81 if it's Winston-Salem specific. All right, so initial velocity, we have that. Well, I have only two pieces of information here. I need one more. What else do we know about the green ball?
Its height, the displacement is 10. Displacement's 10 meters.
Thank you.
Positive.
Yes. All right. We now have three pieces. We can find the others. What information do we actually need to find here?
Time.
Yeah. Time is the one thing that's linking the two balls. And they happen to be taking place on the same planet. This is what's common to both of them. They're both in the air for the same amount of time. So now we bring out the cake formulas, because the acceleration we're assuming is constant. And we have VF equals VI plus AT. VF squared equals VI squared plus 2A dot delta XS, whatever letter we happen to be using today. I'm using X today. Delta X equals VIT plus 1/2 AT squared. And delta X equals VI plus VF over 2 times time. All right, so we have our four constant acceleration equations, kinematic equations. If you're looking at those four equations and you're thinking, what on earth are those? Then you really need to watch those videos where I talk about cake. Constant acceleration kinematic equations. Spells out cake. I'm trying to find time. I don't have final velocity, so I need to, which equation has time but not final velocity?
Third one.
Okay. So I have 10 is equal to 0 times time plus 1/2 9.8 times squared. In other words, 10 is equal to 4.9 t squared. There we go. And then solve for time, which is 1.5, I don't know, whatever it is.
One point four three.
1.43. Units?
Second. Square. Wait. No, just second.
Just a second, okay.
Second.
Yeah, it's time. I hope it's just seconds. All right, so now we know time, we know how long the ball is in the air. We now have 3 pieces of information for the red ball, and we just need to find this. Which equation do we use? Okay. So I know acceleration, I know time. I don't know VF or VI. It is possible to use this one if you know the trick there. Yes?
Shouldn't the 1.43 be on the green ball, not the red?
It's on both. They're both in the
Oh,
air for
that's
the
right.
same amount of time.
Yeah, never mind.
And so I would say let's hold off on this one and then I'll do the trick right after that. Which one is going to be the quickest? We don't need anything other than just algebra skills. Hint, I'm trying to find VI, but I don't have VF. So I want the equation that doesn't have VF in it.
The third equation.
So if we use that one, we have 0 is equal to, I'll just label it as V times 1.43 plus 1/2 9.8 times 1.43 squared. And you end up with V is equal to whatever that ends up being. So 4.9 times 1.43, it'll end up being negative. So 6.6 or so. And the tension mounts. Somebody's going to just shout out an absolutely brilliant answer that will change everyone's life.
7.007. Meters squared. Meters per second.
Anyone else got the same thing? I got a couple nods here and a couple of something went wrong. But we had at least 3 people who got that. And I know it's going to be somewhere around there. So that's the answer. The other trick on this one is when an object is shot up, in the absence of air resistance here, once it's in the air, the speed of the object is the same at the same height. So whatever the speed is when it's shot up, has to be the same speed as when it's falling at that point, right at the end. The velocities are different because directions are different, but the speeds are the same. So if whatever V is, VF is the negative of that. So we could have used the first equation if we had said negative V is equal to V plus 9.8 or 1.43, or times 1.43. And so V is equal to negative 1/2 of this. That's the other way to have done it. Yes?
When we're doing a question like this on a master set or a test, how many significant figures would we report the answer in?
Enough so that you convince me that you know what you're doing.
Okay.
I'm not worried about significant figures on the test, only on the first plat.
I did mine, I don't wanna confuse anybody, but I did mine differently, but I got the same answer, like I used.
It is very rare for you to do it the wrong way and get the right answer, so.
Okay, I did, like when I got the time for the green ball, I divided that by 2
For the time and the half, for half the trip?
for half the trip.
Okay.
And then velocity would be 0 at the top, so I used the first equation. Does
That-
that work every time?
Yeah,
Okay.
yeah,
Okay.
you say every time, suddenly trying to
Like-
think of exceptions, but, yeah, on a problem similar to this, yes, that is completely valid approach.
Okay, thank you.
Now, sort of a caveat to it's rare that you make them do it the wrong way and come up with the right answer. In high school, I was taking a calculus test. I made 3 mistakes on a calculus problem and got the right answer. So I do accept that it is possible to do it wrong. Fortunately, my mistakes all ended up canceling each other out. All right. I am going to stop it right there. If you have other questions when you're finished with the lab, then you can ask at that point. Let's head on down to the other room. The other room being 306. I believe I left the door open. It's just easier than hauling the equipment in here. I don't know how much of that got caught, but hopefully enough.